All right, guys. Today I'm going to start with like it's going to sound silly, right? It's going to sound like I was joking about with Sarah. Like this is going to be sound like something from Sesame Street. Uh, but it's so common in terms of mistakes that I felt this is the first thing we should lead off. The difference between, and actually it segues into reference and perspectives and stuff, but the difference between right and left. And again, I know what you're saying, like, come on, dude. But your right and your left is different from you looking at someone and their right and their left. So how many times back in the day, someone would come into an emergency room and the instructions were amputate right leg immediately. And the doctor would chop off the wrong leg because it was their right leg and the doctor chopped off, and probably the doctor had been up 80-something hours and was hopped up on stuff back in the day. But mistakes like that happen. Your right, my right, sometimes it doesn't line up. If we were standing face to face and I said, point to the right, you point this way, not face this way, right? So how do we, and then right means correct. So rights and lefts and stuff sometimes be very confusing in our world of kinesiology. Good morning. So what I'd like to do is set a precedent. When you guys took biology lab, you had to identify certain bones and you had to identify like which side, like is that a right femur or a left femur or a right humerus and left humerus. You had to look at landmarks and stuff. So all I'm trying to show you is that this is a right humerus and this is a left humerus because it's from the skeleton's perspective, right? Like, you remember that in biology? So if this is a right humerus, even though it's on your left, it makes sense that this would be a right shoulder, a right elbow, a right wrist. It's from the person's who you are observing's perspective of right and left. So on the test, if I say, what motion did you observe? This is left elbow flexion, even though it might be your right. It's like my mom used to tell me, it's not about you, right? It's not always about you. So it's a common mistake, rights and lefts. So just remember, just like we did in basic biology lab, how we analyzed it from the bone's perspective. And this is what's cool. It can be from your perspective if you mirrored the person you're analyzing. So if you see this, you could become that person and do that. That's not a problem. Y'all are both seeing the same thing. But we have to remember, when you're going to be working with patients, when you're going to be working with athletes, when you're going to be working with children, when you're going to be working with older adults, it's their body, it's their perspective, it's their joints, it's their muscles, it's their movement. So it has to be from their perspective. Does that make sense? Okay? Common mistake, like on tests. Common mistake. That's why I wanted to bring it up first. All right, that is not what I wanted to do. Yoink. This is what I wanted to do. All right, guys. There are two main types of movement. We're going to try to keep everything as simple as possible. Y'all are mostly familiar with linear motion, straight line stuff. When you've had physics class in high school or college, it's always been applied to up, down, front, back, left, right, F is equal to ma. All that stuff has been applied through linear movement. But we also have rotational concepts, rotational world that doesn't get as much love, that we have to understand, we have to talk about, we have to learn, we have to develop, because that's how our bodies move. We rotate in order for things to translate. But what our joints, wrists, elbow, shoulder, what they cannot do on their own normally is to translate, because that would mean your shoulder joint here, for it to translate, we would have to do things like this. That doesn't look good, right? We don't translate joints. We have to rotate in order so that something can stay connected to something else. We rotate joints, such as elbows and shoulders, so that we can translate certain parts of our body. That's not a problem at all. I'll give you an example. My major professor at Auburn, Dr. Weimer, was a 4th-degree black belt in Taekwondo. So she would do this analogy where she would say, if I was going to throw a punch, my hand would translate forward, but only because my shoulder is rotating at the same time as my elbow. But if the shoulder and elbow rotated independently, it would look really ridiculous and silly. It would look something like this. Or my favorite is when you do shoulder first. But when they happen at the same time, you get translation of a certain part, like a hand or a foot, but that's only because our joints rotate. We rotate to translate. That can be a big illusion because our instinct is to want to look. Here's to me a good example. In football, I'm guilty of it. I just watch the ball. I'm just watching the ball. But people who know football are watching like the linemen, and they're watching things, not distracted by just the ball. And that could apply for a lot of different sports and skills. I'm just using football. Human movement's very similar. We get distracted by certain things that our eyes want to focus at. But the real magic is happening behind the scenes. Does that make sense? So for us to translate segments, we have to rotate joints. We rotate to translate. Hey, even translating my body across the room, I have to rotate things. I have to spin things in order to make my center of mass linearly go across the room, linearly go up and down, linearly go front and back. This is the football. Your eyes want to follow the football, but I need to get you guys to see where the magic is actually happening so that we can analyze those things about which rotates in order for us to translate. Does that make sense? To me, the easiest way to differentiate translation and rotation, just like anything else, it's a spectrum. You have pure translation, straight line movement, no spin at all. Pure translation would be something like this. Just from the perspective of the pipe, just moving across the room. Pure translation, pure straight line motion. It's going somewhere. If you're moving in a straight line, you're going somewhere. Pure rotation is every point, and again, I'm summarizing to try to keep things as simple as possible. Every part of an object, we call it rigid links in biomechanics, is moving or orbiting about a fixed point. That's what an axis is. That's what a fulcrum is. So in this regard, pure rotation would look something like this. If you asked yourself a simple question, is it moving? Sure. Is it going somewhere? Absolutely. Now let's do it to the rotation. Is it moving? Sure. But is it going anywhere? No. That's the big difference. Think about a merry-go-round. You're on a merry-go-round and it's spinning. Is it moving? Of course, but is it going anywhere? No. And that is the biggest kind of eyeball test when we talk about movement. Is my elbow moving? Yes. And the center of mass, center of gravity, is going somewhere. The center of mass of my lower arm is going forward, but then it's going back. But the connection of my ulna or my humerus isn't going anywhere, right? And the combination, and this is, see, pure linear, pure rotational, and this is the one, guys, general human movement. And when I say general human movement, it's general movement, because I'm going to give you examples like the wheels on your car and other examples. It doesn't have to just pertain to humans. It's just we're here to study human movement. The combination, pure translation on one end of the spectrum, pure rotation on the other end of the spectrum. Life is a combination of everything. So general motion is a combination of translation and rotation. And guys, that's what we do most of all. It's some combination of, are you moving? Yes. Are you going somewhere? Kind of. I'm going to give you a lot of examples. Okay? I've already established that my shoulder cannot move in a pure straight line. Now, when I say move, again, I'm not talking about like, well, if I go forward, my shoulder's going straight. Okay? I'm talking about the actual bones that articulate the shoulder and how they move relative to each other. So when I say the shoulder can't move in a straight line, what I'm trying to say is the humerus relative to the scapula can't do this. It can, but that's what we call in athletic training a bad day. Okay? And I've seen it several times. But this is what we can do. We can take our shoulder and we can do something like this. We call that abductions, right? But think about it. We had a combination of things because we had rotation about a fixed point, the shoulder, but we also had some translation. And I know that because my arm, the mass of my arm, started to go out and up, but then it started to come in while still going up. Does that make sense? Or for our shoulder, if I did this, it's going forward and up, but whoa, eventually it's going to go back and up because it's rotating. So it's a combination of straight line, forwards, backs, ups, downs, and spin. And the way we communicate spin is clockwise, counterclockwise. I know you've heard that. I know you know that. Clockwise, counterclockwise, positive spin and negative spin. In our body, we have versions of clockwise and counterclockwise that we're going to call flexion and extension, abduction and adduction, external and internal rotation, right transverse cervical rotation and left transverse cervical rotation. All of those different names of specific motions are variations of simply two different ways to spin. Make sense? If you could spin one way, you got to be able to spin the other way. Now, unlike a car, if you're changing the oil and the car's off the ground, the tire, you could spin the tire on a bicycle. You lift the bicycle up, and you can spin the tire, and it can infinitely keep spinning in one direction or the other. We have limits to our range of motion. We can't just keep spinning the tire. Again, illusions. Well, what about stuff like this? That's a combination of stuff. I flex until I can't flex anymore, and then I actually rotate my trunk, and then I start to bring it back down, and then I reposition so I can bring it back up. So your joint can't just keep spinning. So it makes sense that if I'm gonna flex again, I gotta extend at some point in order to flex again. You're mostly familiar with it when you walk. When you walk, you're gonna heel strike. Then you're gonna transition to foot flat, that's plantar flexion. Then you're gonna dorsiflex flex. Then you're gonna plantar flex again. You have to recock in order to have plantar, dorsi, plantar, dorsi, plant. You gotta keep recycling it. Right, then left, then right, then left. Two main types of motion, pure translation, pure rotation. Different segments of the body can translate, but we move by rotation. And those rotations are going to happen. We're going to talk about it next, planes and axes. And it's important to understand these rules so that we can help to identify and interpret illusions of motion, hard to see motion. Guys, I know y'all been introduced to flexion extension. But have you been introduced to things like left transverse pelvic girdle rotation because of left hip internal rotation? And a lot of the advancement of being able to see human movement is by learning the rules, so that then you can understand, oh, that's why that's what it's called. That's why that is what it is. Okay? Sarah, do you want to add anything in terms of things that you've seen in your study groups in the past semester about these concepts?
It's kind of acceptable.
Yeah? Accept the rules. Okay? So, objects in terms of rotation, because that's what's going to be important in this class. One of our commandments, and when I say commandments, I just mean points that'll help you not make as many mistakes. Verse 1, we don't assume. Guys, it's so just like the doctor that amputated the wrong leg. Assume, right? Just assume. We make a lot of mistakes by assuming. Do not assume. Double check. Make sure. Okay? We rotate to transit. I just taught you that. Check that box. We rotate joints in order for us to translate things on our body. Joints rotate in a plane about an axis. That one is super important. Because I think planes get a little confusing for people, and I'm going to try to take time to explain why, how planes could be a view of something, but for our world, planes are a rotational dimension about which we can spin in. That's what planes mean to us. And if anything is spinning, that means it has to spin about something. That's what an axis is. Okay? If I don't have one, but if I had a basketball, I promise you, and I could spin it on my finger like a globetrotter. The ball is spinning in a rotational dimension, but it's spinning about a fixed point. Okay? So that's what that kind of commandment is about. Okay? We rotate, joints rotate in a plane and about an axis. Okay? And the rest of them will come about in time. Guys, if I mention it, if I talk about it, it's important. Okay? It's important. So on the test, I might ask you what general movement is. Okay? In the little notes, it says general human movement. But guys, general motion could be for anything. Like I said, your bicycle is rolling, your car, your vehicle, the bus. If I asked my youngest son, hey, Brian, is the bus translating or rotating as it comes across? He would say, well, it's translating. It's moving in a straight line. But the wheels have general motion. Think about it. The wheels are spinning, but they're also translating, right? The wheel itself is a combination. For the wheel to just be spinning, the bus would have to not be going anywhere. If you get stuck in the mud, and your wheel's spinning out, that's pure rotation. You're spinning, but you're not going anywhere. But if you get unstuck, that's general motion. And what's cool is, and this is what I'm going to try to teach you and emphasize, straight line world and rotational world have two different ways of explaining their movement. In other words, we talk about them separately. Straight line world, linear world, translational world, we have terms like up, down, front, back, left, right. In mechanics, positive X, positive Y, negative Y, positive Z, negative Z, north, south, east, west, displacement. Like, we have terms for that. What you guys don't get introduced and developed a lot is the terms we use for rotation. Spin. How do things spin? So when the bus is moving across the road, I can look at that bus and say, hey, the bus is traveling south. That's a linear world. But I could also look at that wheels and say, well, how would I describe how the wheels are spinning? Clockwise, counterclockwise. You see, there are different rules. I wouldn't say the bus is traveling south clockwise, in other words. Give unto Caesar what is Caesar's. Straight line things require straight line conversations. And rotational things require rotational conversations. And that to me is where most people get confused, and it's not your fault. You, and when I say you, I'm saying generally, want to describe rotational things in straight line words in conversations. You have been introduced to joint motions with straight line concepts, and that's unfair to you. I'll give you an example. Arms go out is abduction. Out is a straight line concept. Or how about this one? Leg goes back is extension. That's a straight line word. Up, down, back, front, side, side. But extension, flexion, abduction, that's a rotational concept. So we're taking rotational world and we're using linear words, and that doesn't work. A couple examples of what I'm trying to say. How many of you have ever heard abduction is movement of the shoulders away from the midline? Yeah? Yeah? That works great until you're not going away from the midline, until you're coming back to the midline. That's still abduction, because abduction isn't a straight line concept. Abduction is a rotationary concept. So on the test, I'm going to ask this question. I'm going to be here, and I'm going to do this. And I guarantee you, several students are going to say bilateral shoulder adduction because both went to the midline. You see what I'm trying to get to? No. This one rotated this way, and this one rotated an entirely different way. They're in different places, right? So that's like saying we're in Lafayette, one went to Breaux Bridge, and the other went to Crowley, so they must have been traveling the same. Doesn't that sound silly? Another one people are going to miss because of the unfairly being introduced to rotational concepts with linear verbiage and linear world is this one. Leg goes back is extension. You've heard that one before? Or leg goes forward is flexion. So if I pivot about my right hip and my left leg stays straight, in other words, let's pretend my left hip is in a cast. I couldn't move it if I tried. I could not have hip motion in my left hip if I tried. You ever saw in Despicable Me cartoon, right, with Gru? Freeze ray! Couldn't move it if I tried. I could pivot. I know that's really cheap. I can pivot about my right hip and my leg goes back. My leg went back, but I didn't move my hip. My leg went back, but my hip stayed in anatomical position. But you are so used to using linear words to describe a rotational concept that some of you are going to say, I saw the hip extend. When my left hip didn't do anything, it stayed in the exact same position. Straight line, anatomical position. This hip is still in anatomical position. You see what I did? Leg went back, but the hip didn't move. You see what I did? You would put, well, first of all, that is a great question. The answer is what I ask, right? So in other words, on the test, I might say, hey, where was there motion? There was motion at this hip. Yeah, this hip went from straight to flexed, all right? I'm going to teach you that. The point right now is we can't assume. We can't use old verbiage like ups and downs and fronts and backs to describe rotational concepts like flexions and extensions and abduction and adductions. That's the main thing right now. Yes, sir? That is a question for another day, but they don't have to. I can extend my hip without my glutes contracting. I'll give you an example right now just because you asked. I start here, I'm using the muscles in my front, right? The glutes are in my back. I could extend my hip and it's still these muscles in my front that let it down eccentrically. So that's another great example if we don't assume. That's a big deal on exam number 4, because you have been introduced to, if you see a certain motion, it must be because of certain muscles. And that's not how the world works. Just because the elevator is going down doesn't mean something's yanking it down. Something actually pulling up and letting it go down, right? Controlling the speed about which it goes down. That's another illusion. Glad you brought that up. So what I'm trying to explain is that it's gonna make sense. Don't take it hard. Don't take it personal. You've only been introduced to these rotational concepts through linear words. No wonder it's complicated and tough. You've only been taught forearm goes forward, that's flexion. Yeah, unless it's not. Unless it's not going forward. Unless it's going back, that's still flexion. You see what I'm trying to get? So when we say don't assume, it's don't think because you had a freshman level class that kind of dabbled in human movement. All I'm saying is don't think that that's gospel. And I'm trying to explain why. Because they probably used linear words because it's easy. It's easy to use front, back, left, right, up, down. That's not how it works. We have to use rotational concepts to describe rotational things. And we use linear concepts to describe linear things. Cool? Anything to add?
I think your bus analogy was pretty good for setting them up for how tricky questions can be sometimes, because his answer had to do with the wheels, and he didn't ask about the wheels. He asked about the bus. And to understand how the bus works, you have to know how the wheels work. So like that can be, he's not going to ever ask about a bus in a test, but he's going to ask about
Maybe.
the joint. Yeah, but he's going to ask about the joint. So you have to, you're not assuming he's asking about the wheels. You know he's asking about the wheels because he's asking about the movement of the bus.
And for those of you that couldn't hear, Sarah brought up a great point about when the bus is moving across the street, we have to not just assume everything is about the bus, because the wheel, think of it like this. You could replace the wheels on the bus. You could have a different set of wheels for the same bus, because it's not about the bus if I'm asking about the wheels. Okay? So the analogy is, if I'm walking across a class, like the bus is traveling across, your instinct is to just want to see me, like my center of mass, just me as a whole person. But we have to get you to see the wheels. We have to get you to see the wheels. We got to get you to see this. Make sense? It's almost like if the bus was going slow, instead of you being at a fixed point and seeing the bus move across, it's almost if the bus was going slow, you're walking with the bus. So you don't actually see it moving at all translatory, but you can see the wheels spinning. Does that make any bit of sense? That's what I need you to get you to see. I need you to see not what's happening like this. I need you to see what's happening here, regardless of if I'm moving or not in a straight line. Good feedback. Guys, I give you on this slide, I give you some examples of translation and rotation. That's all it is. It's just examples. Straight line, spin, and combination. In my opinion, one of the best lessons that I've ever learned about human movement analysis is not to eat the apple in one bite. If you've ever seen The Matrix, if you've ever seen sports where there's all these complex movements, it's not. It may look complex because you're following the ball. The elbow can only do 2 things. The wrist can only do 4 things. The shoulder can only do so many things. Every joint can only do so many things. So even though we see something that looks crazy and complex, all we got to do is say, no problem. Where do I want to start? What did the ankles do? What did the knees do? What did the hips do? What did the trunk do? What did the shoulder do? Does that make sense? The Etch-a-Sketch. Y'all know what an Etch-a-Sketch is? I love this analogy because the Etch-a-Sketch only has 2 knobs. And think about it. The knobs rotate, but the little magnet translates. It's only 2 knobs, but yet some people, not me, can do incredible artwork on the Etch-a-Sketch. 2 little knobs. The symbolism there is us. We only have so many knobs, but we can do amazing, beautiful things. Gymnastics, football, basketball, baseball, occupational work, play. We could do some amazing things with some simple knobs when they're working together. So the secret is, when the knobs are working together, you're going to see all kinds of crazy stuff happening, but I need you to not look at that and focus on the knobs. How is this knob turning? How is that knob turning? Does that make sense? A lot of distractions with human movement. We rotate to translate. I'm going to talk about functional circle of sight and reach. My last group, Sarah's part of this semester's student group. I do this every semester, starting way back in 2023. But they help by doing like little YouTube clips and improvements of the little QR code. If you scan it, it'll go to my last semester's class and get some examples of some of these concepts. Okay. What in the world is a functional circle of reach and sight? Guys, super simple. That is our Etch-a-Sketch pad. That's the borders about which we can play with our knobs. Our functional circle of sight and reach is literally like, how far can my hand go forward, up, right, down, up? So if you think about it, it kind of creates this circle that we can make to move in. Like a bubble, right? And to me, the coolest thing is the illusions that go into how far I can reach forward. Like if all I did was flex my shoulder, let me get here so that people watching on the stream can see. If all I did was flex my shoulder, like I feel like a T-Rex. Like, look at how much extra my scapula provides for me going forward. That's not shoulder. The shoulder didn't do this. The shoulder didn't dislocate for me to reach forward. That was something different. I could also reach further by like rotating my whole body across to reach forward a little bit too. So functional circle is like being able to put your hands in infinitely many positions. Let's apply it to sport. If a pass is thrown to a wide receiver, wouldn't the wide receiver want to be able to get their hands in infinitely many spots because you never know where the ball's going to be? So you have to position your hands accordingly. Baseball, same thing. In fact, it's kind of this transition that we say you kind of get handcuffed, right? I don't know whether to have my hand here or there. It's kind of in the middle. So functional circle is just a concept of, man, we need to be able to move our parts to be able to defend ourselves, work, grab, catch in this bubble that we have. Sight, functional circle of sight, means I need to get my computer screen to be able to see in as many places as I can. I can't rotate my head to see the screen, but you know what I can do? Rotate my trunk to help, rotate my pelvis and my hips, and now I can see behind the screen. The different knobs that can be used to help me achieve sight. And it's not just looking behind you. Sometimes you need to keep your eyes on something and reposition your whole body to either move. So in order to keep your eyes on something, you may need to rotate in order to keep your eyes locked on something. That's a big illusion. Did my neck move? Well, sure it did. However, you've been introduced to when the neck moves, like your eyes move or your nose moves, linear. But I'm going to show you that sometimes your neck moves and none of that stuff moves. My nose is lined up with my sternum. Now my nose is looking at my right shoulder. How'd that happen? Because I had to look to the right in order to get there. Make sense? So we're going to have these functional circle tasks that I'm going to use these concepts. So think of it. Your functional circle, in order to keep you looking one way, you may have to rotate your neck when your whole body is trying to spin the other way. Not all movement. In fact, majority of human movement is not, I call it robot world. The things we do is in these kind of combinational things. And I'm going to teach you guys, I'm going to teach you, trust me, I'm going to teach you how to see, which is hard to see. I promise you. Trust the process. All right. Here we go. Planes of motion. Let me ask you this. Anytime you're talking about human movement, the term plane and axis comes up. You ever think about that? Like, what, planes and axis, planes and axis, planes and axis? Don't get caught up so much with the planes right now. Think about the axis. Axis was associated with spin. Remember that? Something can translate and not have an axis. The bus, the center of mass of the bus, can travel south. No need an axis, but the tires have to spin about an axis, right? So just the fact that we say planes and axes, that should be a clue, a light bulb that says, oh, planes, when associated with axes, that's spin stuff. That's rotational stuff. We're in rotational world. Does that make sense? Planes and axes. Ooh, there's an axis. There's got to be a spin. There's got to be a rotation. I'm going to jump ahead to what planes are not in this class. A slice in space. This is page something. So planes, because think about it, guys. If you've ever seen like a person in anatomical position, Vitruvian man, and they have planes and axes, there's no movement because it's on a fixed piece of paper. It looks very straight line, is what I'm trying to say. And so a plane without an axis is literally a two-dimensional view of something. It's like if you were going to watch a movie, you'd want to view the movie here. You would not want to view the movie here. So it's not that the concept of plane can't be used in the medical world, but plane by itself is a view. So give you some more examples, right? This is a lateral view of an MRI. How would you want to see it? How would you want to see the side of the brain? You'd want to look at it from the side. How would you want to see the front of the brain? You'd want to look at it from the front. How would you want to see the top to bottom of the brain? You want to look at it from the top. It's a view. So a lot of times you'll see a lot of commonalities, guys. A lot of times people confuse plane and axis because we're so used to thinking of things linear, straight line wise. So when you see the traditional sagittal, frontal, transverse, know that those are views. But when we say plane and axis, it's about the spin. Where is my baseball? So check this out. This baseball can move in 3 dimensions of straight line motion. We have words for those, X, Y, Z. In each dimension, it can move 2 different ways. So in other words, this is the Y. It can go up, down. Easier way to look at it. Interstate 10 is one road, right? I-10, but it could go east or west. I-10 East is just as much Interstate 10 as I-10 West, is what I'm trying to say. It's still I-10. The Y dimension is one road. Going positive or negative is just two different directions of motion in the same road. Yes? So in terms of straight line, we have three dimensions. You watch a movie in 3D, you get the two-dimensional view, and you get the third dimension coming out, which is specialized. Y, X, Z. 3D, straight line world. A visual view of a plane has to have two dimensions, two linear dimensions. This screen is two dimensions. We have the Y and we have the X. There is no Z. So a view of something, when you see that picture, notice, sagittal. Ooh, that's made up of Z and Y. There is no X. Frontal. Ooh, that's Y and X. There is no Z. Transverse. Ooh, that's cool. That's Z and X. There is no Y. But when we give it spin, cool things happen. Planes and axes. Objects only rotate in planes, but now there's no confusion. This baseball can spin in a given plane that we call the sagittal plane. This baseball can spin in a given plane we call the frontal plane, and this baseball can spin in a given plane we call the transverse plane. Planes and axes. If the baseball spins in a transverse plane, it has to spin about an axis. We're going to give a name to that next week. If the baseball is spinning in a certain plane, it has to spin about an axis. And if the baseball is spinning in a certain plane, it has to spin about an axis. So planes for human movement, because we rotate to translate, all of these rotations have to occur in planes. Our body joints rotate in planes, and thus they have to rotate about axes. So for our world, planes are going to be associated with rotations. How would this person have the spin in a sagittal plane? Do I have any physical educators in there? People want to work with kids? Think about it. Think of the ways you can ask a kid to spin. I'm not even talking about joints. A kid could do a front roll or a back roll. That's a certain dimension of spin. We're going to call this sagittal. Think about that person right there doing a front roll or a back roll. You see how like the sagittal plane kind of shows you how they would be spinning? The rotational dimension. What else can we ask a kid to do? A cartwheel. That's a spin. If they do a cartwheel, wouldn't their body spin? Look at that frontal plane. Wouldn't that kind of represent a cartwheel type spin? Yeah? And the third way we can ask a kid to spin is like this. Spin to your right or spin to your left. Three ways we can rotate in three different dimensions. Now, what's cool to me is just like in linear world, one dimension, but we can move east and west on I-10. Every dimension of spin, we can rotate two different ways, clockwise, counterclockwise. The kid can do a front roll or a back roll. The kid could do a cartwheel to the right or to the left. And the kids could spin to the right or to the left. You see how there's similarities? There's a ton of similarities because they are similar. It's just one is discussing linear and the other is discussing rotational. And the biggest problem that I'm trying to help you guys to see, and it's not your fault, is in the past, you've been discussing rotational world without even using the words you should use, and that's unfair to you. I can see how this stuff is confusing. Like, that's not even fair. That's like trying to talk about basketball using football terms. If we're going to talk about rotation, we have to use rotational terms. And if we're talking about translation, we have to use translational terms. Simple? Yes, ma'am. The sagittal plane, now keep in mind, I haven't taught this yet, so this isn't your fault. What I am going to teach you is that the link between linear and rotational is our axes. Axes are straight lines. So sagittal plane spin is going to occur about an x-axis, but we're going to call it the bilateral axis. Transverse spin occurs about a fixed straight line that goes up and down, like our y, but we're going to call it a polar axis. And frontal plane spin occurs about a straight line that comes front to back, like our z. We're going to call it an anterior posterior axis. You're very welcome. You're very welcome. I love the way your brain was thinking ahead. Okay? Sarah, do you have anything to add before we close shop? What can they study, or what can they emphasize? What can they do? Like I always say, if you're awake, you can practice. If you're awake, you can study. If you're awake, you can develop these concepts.
Kind of like, remember in our class, you had said, we don't use these pictures, like it's better to think about it and look at a picture, because a picture's like a textbook, and a textbook is 2D rather than 3D. So if you're looking at this picture, for instance, and you had like no explanation, you didn't know how to talk about this, you might think that those colors are cutting it in half, and that might be the axis. But I remember whenever I took this, I made a note that maybe on the top, I would do an arrow going forward, and then on the bottom, I'd do an arrow going backwards. So you can see the spins through those colors.
So what Sarah's saying is that give it motion.
Yeah, give it motion.
So like if you're looking at a two-dimensional picture, give it the spin that it needs to make planes and axes actually mean what they mean. Planes and axes mean spin. So to Sarah's point is, if you don't spin it, it may not make sense. You have to give it the motion, maybe to help practice.
And if you have like a ball at home, maybe practice spin and put like a pencil or something through it, so it's moving about the pencil, and like your pencil becomes the axis. Does that make sense?
Yeah. So I'm gonna tease what's coming next week. So this clock, the hand on the clock, would be rotating in a specific plane because it's rotating about a specific axis. So I'm going to show you how does the axis run. Don't start with stuff we're not familiar with. Start with stuff we are familiar with. How does the axis run? Ooh, that's kind of like our Z, front to back, anterior to posterior. Isn't this the front of class? And that's the back of class? Anterior to posterior. So the only way this clock hand can spin is about a frontal plane, because it's spinning about an anterior posterior axis. But if this isn't spinning, the clock cannot move in a plane. The clock is not moving in a frontal plane. The clock is not moving in a frontal plane. It has to have spin with an axis to be rotating in the plane. Yes, ma'am. It would be, what a great question. If the clock, no, you're plane, it would be rotating about an X. And again, guys, this is just foreshadowing what's coming. I'm going to lecture on this. I'm going to teach it. We're going to practice it. But I need to make clear on this first real lecture why things may be confusing. It's because in your whole life, I don't mean to assume, maybe you went to a great physics school, but people have used linear terms to talk about rotational concepts, and that just doesn't work. If you do that, things are going to be very confusing. Away, oh gosh, it's coming back. That's the thing. All right, guys, y'all have a good weekend. We'll see y'all Wednesday, right?